Okay, so I'm going to apologize a little bit ahead of time here, because this is going to be a little out of order in how we do things today. Unfortunately, you know, given like a day to sort out my entire unit has been a little bit tricky. So this one is going to be a little out of order. We're going to do angle of insulation first. I'm going to take you to some diagrams within the notes that deal specifically with angle insulation. Then I'm going to show you the independent practice. We're going to do a couple guided questions. After I do that, I'm going to create another video using the same documents to go back and talk to you about climate change, and then take you to something called temperature lag, and then take you to El Nino and La Nina, and then we'll have another set of guided independent practice questions that are related to climate change. Okay? So let's get this thing started off. Angle of insulation. Insolation, not insolation. Insolation is the stuff you put in the walls to keep you warm in the winter, and maybe so that the heat stays out in the summer. All right? Insolation is incoming solar radiation. Kind of try to break it down in a way that you might be able to remember it. All the words for insulation are in this phrase here. All right, so the greatest factor determining an area's climate is that place's latitude. We've talked about that extensively in the last video. Now I have to talk to you about how and why that's the case. So we'll bring Earth back for this one, and we'll try to discuss how that angle changes depending on where our Earth is around the sun. So here we've got 3 images of Earth. We have our sun, and there's radiation from that sun coming off and hitting the Earth. For this example, don't be alarmed. We don't have 3 Earths. There's 1 Earth, but this is showing Earth in its positions throughout the year. So let's start with this one here. So this top diagram, it is winter in the northern hemisphere. So the northern half of this is experiencing winter. I've also gone through and have labeled that each of the major latitude lines are here. Tropic of Cancer, Equator, Tropic of Capricorn. So when we are in this position, and our tilt always being 23.5 degrees, the northern hemisphere is tilted furthest away. So here, as if you got the sun shining on us right now, we are tilted furthest away in the winter, and this area is receiving the least amount or the lowest angle of solar insolation. The place that's receiving the most solar insolation and has the highest angle is down here, the Tropic of Capricorn, during our first day of winter. So on the first day of winter for us, we are receiving the least amount of sunlight. But on our first day of winter, down here is their first day of summer. They will have the highest angle of solar insolation. And again, the angle of the sun's rays hitting the earth with the surface of the earth, that angle is the angle of insolation. So keep that in mind as we discuss and use these examples and diagrams. All right, here in this case, this is going to be our summer in the north, and it's going to be the first day of winter in the south. So the most intense angle of insolation from the sun will be at the Tropic of Cancer. We have slightly lower, but it's still more than winter, and it's more than spring or fall. So here is the most, it's lower, but down here, this is the least amount of solar insolation in the southern hemisphere on this day. Right? And generally during the seasons, this is slightly changing because our Earth is moving around the sun a little bit every day. Okay? About 1 degree every day of the year going around the sun. So here we have equinoxes. So this is the autumn and vernal. So vernal is our scientific way of describing the calendar year. for spring, and autumn we say for fall, because to be honest, we're in a temperate climate where leaves fall off of trees due to the seasonal change. If you go to places like the Amazon, their leaves don't change color because their temperature and climate stays relatively consistent. So you don't get that huge variability in seasons that cause leaves to fall. So the leaves fall here, but they don't fall everywhere on the planet. Right? Same idea with the vernal equinox. We call it spring because we're coming out of a period of time where we see very little vegetation, and that stuff springs back up. Same idea elsewhere on the planet. Maybe that plant life didn't die, so you don't have anything re-springing up the next year. Re-springing up. All right, so anyways, we've got multiple situations for Earth's orientation compared to the sun, and that changes its angle of insolation. Just to make sure we highlight here that during these times there is equal insolation across all latitude. So there isn't going to be a change. So this area down here in the southern hemisphere equals the same latitude in the northern hemisphere. Both of the tropics are getting the same angle. The only difference is in the north, the sun's in the southern part of the sky, and in the south, the sun is in the northern part of the sky, because you're looking at the sun. All right, let's go to some diagrams so we might be able to make sense of this silly stuff I'm telling you about the Earth moving around the sun. So let's take a look here. We've got our diagram, and excuse me, and we've got the sun here. Make sure you label it. This is our sun giving off radiation, okay? And it is incoming into our Earth, and will have an angle. So here, good idea to make sure that we're talking about 23.5 degrees. That stays constant. It does not waver. We're not going to talk about precession unless you want to talk on the comments about it. I'm not going to do that separately. So here we've got each position that the Earth will be around the sun. Notice though how Earth, the pole, is pointed in the same direction. Everywhere around this diagram, this Earth is pointed that way. Do you remember? All the way back to the beginning of this year. Latitude and longitude. If you want to find the latitude of a place in the northern hemisphere, do we remember? Do you remember? Polaris? Of course you don't. Of course you do. Yeah, you know. All right, so if you notice, we're always pointed in this direction. Yes, we're always pointed at Polaris. Well, we'll do it like this. Good old smartboard, not being smart. All right, so it's all pointed at Polaris. So we are not changing the direction our tilt is facing, but we are changing where we are around the sun. So from here to here, the angle that the sun is going to be hitting the Earth will change. Right? So if I want to say I am here, let's pretend you are the sun for now, and you are directly hitting this half of Earth. Everything on that half of the Earth, top latitude, north latitude, south latitude, are receiving the same angle because the sun is directly hitting the equator. Okay? Now, if we were to change that, let's pretend now I am the sun. If I am the sun, I am going to be hitting the northern hemisphere more directly. But the Earth doesn't do one of these things. The Earth is consistently moving around a center location. So if you were to think of the sun being in the center here, if my fist is the sun, it's moving like this. And let's continue that. From here, and eventually to here. And then back to here. So the angle that the sun is shining on Earth is changing, but the Earth's tilt is always in the same direction and the same amount. So the light that's hitting will change its angle based on the position that Earth is. I'll try to put a simulation down below for you to view that so you have a better idea. Now, let's also talk about the amount of daylight. So here on an equinox, you're going to have 12 hours of day and 12 hours of night. So that happens at the September equinox, which is the autumnal equinox. This also happens at the March or vernal equinox, so it's 12 hours day. It's just not wanting to work with me today, is it? All right, and 12 hours of night. Okay? Get a little R in there. All right, so over here, we're in December, so this is the winter, this is what's referred to, the winter solstice. Okay? Most, if not almost each year, these dates tend to fall on the 21st to the 23rd of the month. So it'll be December 21st to December 23rd will be the first day of winter usually. For autumn, it'll be September 21st to September 23rd. That gets in. The reason for the variability is because the amount of time that it actually takes us to go around the Earth is a little bit shorter than 365 days. So that's why we have to do a leap year so that our calendars stay lined up with our astronomical year going around the orbit once around the sun, all right, revolving once. So here we tend to have greater than 12 hours of night and less than 12 hours of day. And that's going to vary because depending on what your latitude is in the northern hemisphere, the closer to the equator you are, the closer to 12 hours you will be. Because at the equator, it's always 12 hours of day and night. So no matter what the season, equator is always 12 hours day and night. So for us, we're going to have less than 12 hours. And even if you get up into the higher regions of the Arctic Circle and beyond, it's like dark. It's nighttime for 24 hours. So for about 30 days, about 15 days before the winter solstice, about 15 days after winter solstice, it's pretty much pitch black in northern areas of Alaska, okay, anywhere near the North Pole. And it takes a long time for you to eventually get more light. So even though it's 30 days of almost pure darkness, the 15 days even before that and the 15 days even after that, you're only getting a couple of hours of daylight. Let's go over to summer. So in summer, we're going to have greater than 12 hours of day and less than 12 hours of night. So if you get 30 days of night, you get 30 days of light. So that whole process is pretty crazy. Yes, they have what's called the Midnight Marathon in Alaska, where you can be racing at nighttime, but really it's midnight and it looks kind of like 5 or 6 p.m. because there's that much light going on. Yes. It's apparently a very bizarre experience, definitely on my bucket list. So the poles on this day, June 21st to 23rd, the June solstice, aka the summer solstice, you can get some pretty bizarre situations where you don't have portions of the earth going to the dark side of Earth in its shadow. Okay? All right, last thing. We have to talk about what this looks like from Earth. So from our position now, not from just outside, removed in like a spaceship, but now we've got to think about what does it look like through the year for our location on March 21st. So the date is an equinox. This is the vernal equinox. And in the northern hemisphere, our sun's apparent path goes through the southern section of the sky. It rises in the east, and follow my arrows. This is the apparent path that it takes as the earth rotates to the east. The sun looks like it's moving to the west. So if you're looking in this direction, it rises in the east, and in New York at our latitude, it hits about 50 degrees above the horizon for the sun. That's the angle of insolation on March 21st in New York City. 12 hours, day and night. Because it rises due east, sets due west, so it covers half of our sky. So the apparent path is about half of our sky. Not more, not less. So we move from March 21st to June 21st. So because we're becoming more tilted towards the sun, it can start to rise up a little further. So if this is where it was rising, if we're tilting more towards it, it can rise in a different position. So in June, it's going to rise north of east. So N of east, N of E, north of east. That's where it can be rising. So literally you'll start to see over time that the sun is rising north of east, and I wish, hopefully we can come back, but normally what I like to try to do is I like to try and put a place mark on the wall to show where the sun is rising, because we are facing east. I like to put something on the wall to show where it's rising, and then we keep marking it out to show that it's going further and further and further north, so you can see that the sun starts rising here, and eventually it begins to change and move more north until we reach summer. And you can see how the shadow and the cast of light hits different parts of my room. So it rises north of east, sets north of west. This is part of the reason why it gives us a longer day. It also is a higher angle of insolation. It's going to be around 73.5 degrees above the horizon at noon. Key thing, this is noon position, noon time right here. Right? Now, as we continue to revolve around the sun, we eventually end up back at autumn, another equinox. So we're rising due east, setting due, D-U-E. So due east, we're setting due west, still the same amount of daylight and nighttime as the other equinox, and we are hitting the same angle of insolation above the horizon. Okay. One thing you can also start to remember after we do this one, I'm going to relate the angle with temperatures, our seasonal temperatures. So December 21st, our winter solstice. Right? Same idea. If we're tilted further away, if this is where the sun was rising and setting in the equinox, now we're tilted away. So it's going to be rising further south and setting further south of east and west. So here we've got this really short path, shortest path, and we're at about 26.5, 27 degrees above the horizon. So we're only maybe here. Summertime, we're here at noon. Wintertime, we're about here at noon, which is why it's darker in the winter. because we're getting less total sunlight than we did in the summer. So this is the shortest day. Here, we're getting around 8 hours of daylight. And that means there's 16 hours of darkness, roughly, or really close to 16. Okay? Shortest path, shortest day. Now let's start to equate temperatures. So when the sun is higher in the sky, we get higher temperatures. When the sun starts getting lower in the sky, we start getting lower temperatures. That's a nice little relationship to remember. Something also that occasionally comes up from time to time is that there are shadows cast by our bodies from sunlight. And these shadows, and anything casts a shadow, these shadows get longer than they do in the summer. So we have longer shadows in the winter, shorter shadows in the summer, and we have equal shadow lengths on the equinox, okay? Which they're not as short as the summer, and they're not as long as the winter. All right, let's do some practice. All right, now is a good time for us to take these concepts and try to apply them to a couple of questions and see how we do. So go ahead, pause up the video, refer back to these diagrams, refer back to the notes. We'll do these guided practice questions. You'll do some independent practice questions. And then for the next video, we will be using the same document. So go ahead, pause, try these out. Boy, I wish these pauses were a little longer for me rather than going straight through. Woo, this gets exhausting. All right, so figure 1. Let's read together. Base your answer to the question on the diagrams below and on your infinite knowledge of earth science. All right, the diagrams labeled A, B, and C represent equal-sized portions of the sun's rays striking Earth's surface at 23.5 degrees north. Oh, that's some dense information if that's the first time you're reading that. Let's keep reading. We might need to reread the question. All right. So I paused mid-sentence, so let's reread that sentence together. The diagram labeled A, B, and C represent equal-sized portions of the sun's rays striking Earth's surface at 23.5 degrees north latitude at noon at 3 different times of the year. All right. Let's try to figure out what they're trying to say down here. Let's look at this and just deduce our own compare and contrast with these diagrams and then see if any of that starts to make sense, okay? It's hard to visualize what they're writing when it is so dense with information. So we've got A, B, C. To me, each of these plots look like a different place. So we've got 3 locations. It's telling us that these are representing Earth's surface. I've got sun's rays. It looks like it's a beam of light coming down from each, and the beam looks to be about the same size in diameter, but each location has a different angle of insolation. Okay? Yeah, that makes sense. We've got 3 locations. It says equal-sized portions of the sun's rays. That's that diameter area here. Right? We are at 23. So they're striking Earth's surface at 23.5 degrees north latitude. So every location is at 23.5 degrees north, aka the Tropic of Cancer. Things we want to start the flashcard, just in case we need it. All right? So everything here is at 23.5 degrees north, but the angle changes. Okay. I mean, honestly, if it were me, and maybe you too, is once you realize you've got a place, you've got different angles of insolation, you might want to try to figure out what season it might be. So we know highest angle, highest temperatures. Well, our highest angle here is this one, so I'm just going to label that one summer. I don't know if this is going to help me, but I'm going to just label it up quick because it might. I've got this one here, lowest angle out of all three. This is going to be winter in my mind. And we don't need 4 pictures because our equinoxes are same. So what happens in the vernal equinox happens in the autumnal equinox. So this is going to be vernal and autumnal equinoxes. All right, so down here, which graph below, or which graph best represents the duration of insolation at this location, or at this location as the angle of insolation changes? Okay, duration. Duration refers to amount of time. So how long? Well, if it's in the summer, we know we have longer hours. So in our equinoxes, we have 12 hours, it's equal. And then we know we have the least amount of daylight hours, duration of insolation, when it's lowest angle in winter. So I'm going to be looking to see where I have, we're going to say low duration, high duration, meaning less time, more time, just so I can understand the graph a little better. So we've got 90 degrees in summertime, 90 high duration, okay? Low duration. Okay, I like this one so far. This one's telling me that in the summertime we have less time of the sun. Light? No, I don't like that one. This one's telling me it's the same everywhere. This one, ooh, this one would be good for the equator. That would be a good one for an equator question. This one here, that one just isn't gonna work. Oh, you know what? Duration? These would change a lot less. They'd be less than 90. It would be, I should say, it'd be more than 43 and up to 90 for the equator. So they would change this x-axis to represent, so maybe it would be like 90 degrees and like 76.5 degrees. And then you would have it equal across for the equator. I don't want to make you think that these numbers are exactly the same for the equator. They're not. This one's just bogus, I think. All right, let's look at question 2. Oh, Mr. Ryan, why are you giving us these big diagrams? Well, kids, you know what? The Earth is complicated, and it's probably better for us to look at a more comprehensive question. All right, so base your answer to the question on the diagram below, which shows Earth as viewed from space on December 21st. Some latitudes are labeled. There they are, showing us North America. Right there, we got South America right here. Cool, we got the sun's rays, and when they hit, they will be an angle of insolation. So let's look. State one factor other than the tilt of Earth's axis that causes the seasons to change. So we need tilt, but we also need the Earth to move around the sun. But let's use the right word for that from the notes. In practice, we could say that Earth revolves around the sun. All right, so that's a good one. I'd be curious, maybe leave a comment below and give me an idea of what you were maybe thinking for another possible answer here. Don't borrow the ones out of the answer key. I want to see what you authentically came up with, right or wrong, because it is interesting to see what you might manage as you do these questions. So again, finish up the independent practice, use the access points, check your answers. If you've got any questions, leave some comments below, or in Google Classroom, or when we're in WebEx. There's a whole bunch of places. You almost can't not get a hold of me, okay? It's actually probably better than being in class. Probably not, it's more fun being in class, yeah. I agree with you. So, anyways, Next video, I'm going to use the same packet. We got to go back to do climate change, and then we'll go back into do some more guided independent practice questions for climate change. All right, we'll see you soon. Bye.